What's going on, people? Just getting set up over here. I am super bright. That's crazy. It's like a photo shoot. I'm worth it. Let's see. Is my camera going to be upside down again? That's the question. No, we're good. What we got today? Patrick Torreston, Ron. Oh, we got like a bundle of students here, I'd call it. All right. That's not a new light setup. Oh, that'll work. That'll do. It's Thursday on your first week of online classes in the fall 2020 semester. This is a day you will never forget. You'll be 80 years old, and your students, see, look at me. Your grandchildren will be like, Grandpa, do you remember your first Thursday for your COVID-19 2020 fall class? Like, I remember it like it was yesterday, because that is when we did more truth table examples in my discrete math class, my favorite instructor, Daniel Malvo. So if you don't have any questions, we're just going to get started. Okay, no question, not at all. Cool. Let's get going then. So the first thing I want to do is I want to talk about, can you guys see my face, by the way? Someone give me a thumbs up or something you see my face. Does that mean you can't see my face? Oh, good. Okay. Well, you can see the confusion in my face. Thank you, Toru, if I'm pronouncing that right. I'm sorry. But anyway, so first thing I want to do is talk about just some logistic things with the class. And that is, I'm not sure if you guys got an email today. The quizzes I made, if you ever get an announcement saying the quizzes are graded or posted, but somewhere else it says they're not due till like Friday, that doesn't mean it's the final grade. That just means I made the grades viewable. So when you take the quiz and you take multiple attempts, you can actually see what grade you got. It's a whole weird Canvas thing. But anyway, I'm working on figuring it out so you don't get email at all. But don't worry about that if you got that email. But other than that, yeah, boring stuff out of the way. Let's get to the exciting stuff. So the exciting stuff, of course, is math and logic, which are like, are they the same thing these days? Let's find out. So last time we talked about what statements were, and we started talking about logical operations and things like that. And to kind of put this in a little bit of perspective, I want to put this in kind of a context of arithmetic, because there's a lot of parallels between logic and arithmetic, or really anything in math. So let's have, how'd you get over here? Let's have, oh no, oh, okay, let's make a table where we have logic on this side and we have arithmetic on this side. And arithmetic, right, that's just like adding, subtracting, like 5th grade math, that kind of stuff. Can I get this wire out of the way? Ooh, solution, water bottle to hold the water. There we go, there we go. So the last time we talked about statements, and statements are like the atoms of logic. They're the things we're talking about. And statements are to logic in the same way that numbers are to arithmetic, right? Arithmetic's all about doing things to numbers. Logic's all about doing things to statements. So an example of a statement is, let's say, the tooth fairy cheated me 25 cents. There's a statement, depending on the tooth fairy cheated you, it's either true or false. An example of a number, or you could have another statement would be something like 1 equals sine squared x plus cosine squared x. Well, actually, that's not a statement right now. Why is this on its own not a statement? We got a chat. Let's check it out. What's x? Exactly. Perfect way to put it. What's x? Because even though this is true for all x, we haven't defined what x is. If x is a real number, it's true for all real numbers. But what if x is a goat? What if x is a statement? what if X is the Ghost of Girlfriend's Past movie, right? And it sounds stupid, but we have to define what X is. Otherwise, it's a variable that stands for nothing. So F for X, any real number. So now this is the specific statement saying no matter what X you plug in, this will be true. And so an example of numbers, I mean, they'd be things like, I mean, 5 is a number, pi is a number, 2 to the 0 is a number, stuff like that. Now, I'm going to erase some of this, but it's still important. I just want some space. So, statements are to logic like numbers are to arithmetic. They are the things that we play with. Any questions? So then, in logic, we have truth values, which are either true or false. Those are the two possible things a truth value can be. And in arithmetic, we have, I'll say, like numeric values. And so by that, I mean, every statement has a truth value. It's either true or false, one of those values. And in a certain sense, every number has like a numeric value in the sense that like pi, even though we write it as pi, it's a number that equals 3.1415 ... Like it is a number that you can write down, similar kind of thing. This symbol, this Greek letter for p, right? That is the same thing. It's just another way to write this infinite decimal right here. And so it's in the same way as saying I have 5 fingers is another way of writing true, right? It's kind of weird, but that's really what it is. Oh, that was loud. Yeah. I hope it wasn't as loud on camera, which is one benefit of Zoom. It gives you a upper bound on weird noises. But anyway, so we have that. We can keep going with this list of analogies because it goes and goes. For example, in logic, we have binary logical operations. I was going to call them ops, but it stands for operations. And in arithmetic, we have binary arithmetic operations. So in logic, a binary logical operation, the three we've talked about so far are actually not one of them. We'll get to that. But the 3 operations we've talked about, I'm just going to say logical operations. And then there's arithmetic operations. And the operations we talked about are not, or, and. Right? That's not, that's or, that's and. And then in arithmetic, you have things like the negative symbol, plus, and multiplication. So, and we can do an example of these kind of things, right? Like an example of arithmetic operation would be, I mean, you can do just like, what if you did A times B? Actually, we'll get to that. We'll get to that later. But anyway, so far, I hope no one has any questions because we just talk about simple things. These are logical operations. These are arithmetic operations. Let's talk about what an operation really is. I keep saying this word operation, but I don't really talk about what an operation is, other than a fantastic board game that kids probably don't play anymore because they're iPads. They can't make the buzzing sound. But it's also basically, it means a function. So a binary operation, you know what? Let's go to purple. A binary operation is a function that takes in 2 inputs and spits out 2 outputs. They may be thinking spits out, that sounds like a weirdly not professional term to use, but the only other thing I think of is saying outputs 2 outputs, and that sounds stupid to me. But anyway, yeah, so it spits out, oh no, sorry, not 2 outputs, it spits out 1 output. So it takes in 2 inputs and spits out 1 output. So in arithmetic, an example would be the plus sign. So example, you can think of 2 plus 5, for example. you can think of this as really the output of, well, actually, I'll write it like this. Where did I put my thing? There we go. So we know that 2 plus 5 equals 7, but you can really think of that as the output of like a plus function, where in this case, you plug in 2 or 5. Right? Like you guys, a lot of you are CS majors, right? You could literally imagine going to Java or C++ or something like that and writing a plus method or a plus function that takes into inputs and returns whatever the addition of the 2 inputs is, right? This is what it means to be a binary operation. It's binary because it takes in 2 things, and an operation outputs 1 thing in this case. So this is a arithmetic one. So now let's do an example of logic. So logic, you can think of P and Q, right? We said this is an operation. It takes in 2 statements. Like let's say P and Q are statements. Or let's say that. Let P and Q be statements. Then P and Q are 2 statements, or P is a statement, Q is a statement. And then this and right here is an operation that takes in 2 statements, P and Q, and it outputs a new statement, the combined P and Q statement. And so you could think of this as like being the output of a function that I'm going to call and, that takes in 2 inputs, P and Q. Hope this is making sense. This is just what operations are. Now, we start to talk about, well, what the heck is the definition of what's the definition of this and function? So how do we define is the big question. How do we define a binary operation? So we talked about how this, you could think of it as a function in computer science, right? Or a method in computer science. And so if you were to write this method for and, right? What do you need to do to define it? What needs to happen? What do we need to do?
We need to figure out the values for P and Q and then define how it functions based on those values. Like what happens when 1 is true, 1 is false, what happens when 1 is false, 1 is true, all that.
Exactly. Who was that?
It was me, Benay.
Benay, thank you so much. That's so correct. I want to give you a hug, which is a great thing we're online, because if it was in person, I'd give you a hug, and that would be inappropriate. So the point is, yes, exactly. Like if you were to write this function in code, right, what you need to do is you need to define what happens, what's the output for every possible input. So need to specify output for any possible input, right? That's just how coding works. So in our case, can I push this even further back? Yes. In our case, what that means is we can kind of define this and function. And actually, I'm gonna erase that what I just wrote to make some space, but that's what we're doing. So we need to specify output for any possible input. And so we can define our and function here kind of in the following way. Like this. We need to see, so let's look at possible inputs. So let's say our possible inputs are, well, it depends what we're looking at. So if we're looking at P and Q, our possible inputs are, well, P could be true, Q could be true, P could be true, Q could be false, P could be false, Q could be true, and P could be false, Q could be false, right? Those are the four. Oh, I see the problem. If I move that, it doesn't help at all. I need to do this. Is that gonna work? Kind of. Okay, yeah. So these are the possible inputs. And so now we need to define what happens. What's the output? What are we going to call P and Q? What is the output? And so the way we define it for the AND function is we say we want this to line up with our intuition of AND. What it means to say this is true and this is true. And to line up with our intuition of AND, well, if they're both true, we want it to be true. But if they're not both true, it's got to be false because then they're not both true. And so the way you define the AND function is that they're both true, it's true. In every other case, it's false. If just one of them's true or they're both false, we call it false. So this is the definition of the AND function right here. It's not the other way around. It's not like, hey, we have an operation and then we can make the truth table. The truth table is the definition under the hood. Does that make sense? So this is what and means. Like whenever you see me write like P and Q, right, anywhere or something like that, this is what it means. Under the hood, this is what you should be thinking of. Any questions on that? Cool beans. Okay, well, now, then if we have that, let's talk about, that's that. Let's go here. So, now that we know how to define and, I'm very quickly just going to show you a couple more. And so, like our OR function that has P and Q, it takes an inputs P and Q that are statements. What you do there is you have P and Q. Again, the options are true, 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 false, false, true, false, false. And then the output, which is going to be P or Q, that's the output given these inputs, is going to be, in this case, we define the OR function, try to match up with our intuition for OR. And so what that means is we want the OR function to be true as long as one of them's true. If they're both false, it's false, but as long as one of them is true, you're good. And so one of them's true, we're good. One of them's true here, we're good. In this case, where P is false and Q is true, one of them's true, so we're good. The only time P or Q is false is when, the only time we're going to define P or Q to be false is when they're both false, because then that matches up with how we speak in English. All right, so this is literally the definition of OR. This is what's happening under the hood. And then not, it's even easier to define, because this is actually not a binary operation. That's why I didn't want to say binary over here, because binary means you take in two inputs, but the not, it just works on one input. It just flips it. So not P, if the only options for P are true and false. I hope you guys can't see that. I'll just write smaller. The only options for P are true and false, right? And so then not P, which is our output, right? That's going to be, if P is true, the negation of P is false. If P is false, the negation is true. So very quickly, I just want to show you these are the definitions of these operations. And so that's what they actually mean. If you remember from our first class, we talked about when you prove things, you start from truth, and then you connect statements, you link them logically by either observations, definitions, or theorems. Well, these are the definitions. This is how you would link statements if they have and you want to work with that. These are the definitions. Anyway, these are just two examples of an operation. Or three, I guess, if you include the not. But we only have two examples of a binary operation so far. We only have two examples, them being and or. Can we have more? What do you guys think? Or are those the only two binary operations? We could have more, says Benet, and you are correct, right? Because A binary operation is defined by this function. This function, right, that tells you what to do for any possible inputs. So there's four possible inputs to these binary operations, like we saw on the table, right? The true, true, the true, false, the false, true, and the false, false. Didn't even look at the whiteboard for that. The point is, there's those four possible inputs, and any way we define those outputs will give us a new operation. It does something different. So let's work through how you would define one yourself. So, orange is a new color for this. Let's define a new operation called XOR, exclusive OR. Yep. If you guys know anything about computer science and computing and things like that, that'll sound so familiar that it's almost cliche. Let's define a new operation called XOR. It's called the exclusive OR. I'll talk about why it's called the exclusive OR after we do it. But anyway, the exclusive OR, we want it to be true. Now, how do we want? Now, let's talk about what we want this function to do before we define it. We want XOR of PQ to be true if exactly one input is true. So a regular OR, which we're going to call the inclusive OR, that's true if at least one of the inputs is true, like we just saw. But they could both be true. Exclusive OR, it excludes the case, right, where they're both true. We say they're both true, it's kind of false. And this is made to reflect, well, I'll talk about that later. So anyway, let's get to defining it. So the XOR of PQ, right? We need to find what it does on all possible inputs. So our possible inputs are, we have P and Q. P could be true, Q could be true, P could be true, but Q could be false, P could be false, and Q could be true, and then they could both be false. Those are the possible inputs. And now let's look at our output, which I'm going to write as P with a circle plus Q. The circle plus, that's the symbol for XOR. And I'll say symbol is circle plus. So in this case, so let's define what we want to happen. So if P is Q and Q is true, do we want to define the XOR to be true or false in that case? Who's got me?
False, right?
False, right? Because why?
We only want one input to be true, right?
Exactly one input to be true. And in this case, both of our inputs are true, and so that doesn't meet our condition. So we want it to be false in this case. But in the next case, where P is true and Q is false, if you get those inputs, we want the function to output true because, yeah, exactly one of the inputs is true. Same thing down here. Exactly one of these inputs, false and true, is true. And down here, well, we have both are false. So it's not true that exactly one input is true. So it's false. So this is the definition of XOR right here. It's true as long as exactly one of the inputs is true, false otherwise. And so this is made to reflect how we talk in the English language a lot of times. For example, if I say, like, hey, I'm either going to get the steak or the burger, right? What you think I mean probably, is that I'm either going to get a steak or get a burger, but not both. You'd be very confused if I got a steak and a burger. You'd be like, what? You say you're going to get a steak or a burger? And I'd be like, inclusive or, baby. And we'd be like, what does that mean? Because we haven't defined it yet. We're going to define it right now. So, exclusive or, definition right here. Definition, exclusive or is false outputs false if both input statements are true. And then the regular or, hopefully we got that. The difference is the or, which is, we call it the inclusive or just call it or. The inclusive or includes inclusive or, I'll say includes case where both inputs are true. And so if you have P or Q is true, and if you look at the statement P or Q, and both P and Q are true, well, the regular or would output true. It just wants one of them to be true, not necessarily exactly one. And you can see that from the truth table. Because in the truth table, right, right here, the exclusive or, we say if both inputs are true, it's false for exclusive or. But in regular or, if both inputs are true, our output's going to be true. Does that make sense? Any questions on that? Okie dokie. So, the next thing I want to talk about is, yeah, I'll do it over here. Next thing I want to talk about is logical expressions. Logical expressions versus arithmetic expressions. So an arithmetic expression would be something like A plus B, or something like, I'll say A times B plus C minus D times B, or something like that, right? It's just some combination of a bunch of numbers kind of combined together with these binary operations of plus and addition and minus and all that. Logical expressions, same thing, right? It's just a bunch of statements combined together using these logical operations. So we could have something like P and Q, or not R and not P. Something like that, right? And this leads us to the next question I believe Benet asked last time. It's a very logical question to ask, and that is logical. Nice. And that is the order of operations. What's the order of operations? It's like, what does this actually mean? Like when I get to this, do I do not R and not P? Or do I do not R and not P? It's ambiguous until we define it. And so there are order operations, and I think in philosophy it's called order of precedence because they want to be different. But the order of operations is simply it goes not, and then or, in that order. Not, and or. Whereas in arithmetic, we have PEMDAS. Right, we do We do parentheses, exponents, multiplication, division, arithmetic, addition, and subtraction. It's all arithmetic. Here we do not first, then and then or. So an example of that would be, P, by example. Yeah, P and not Q or R. How do you read this? What do you do first? Well, the first thing you do is the not Q. So first, we're definitely going to do the not Q. Think about doing that first. And then what do? We have the and the or. We have the and the or. We always do the and first. So then you think about doing the and then finally you do the or. I hope that makes sense, and we're going to do a ton of examples of it. And I'll do an example of PIMDAS because I think you did that in 4th grade or whatever. So 6th grade? Oh, no. It's been a while. So the point is, yeah, that's order of operations. Any questions so far, any of this? Keep it engaged, keep it loose. How are you feeling? Okay, this will be cut out for the people that watch it later. This is the kind of behind the scenes stuff that all of you guys that show up to these lectures get. So, what time is it? 4:30. So next, now that we know what logical expressions are, let's talk about, I'm going to erase some of this. So we have logical expressions, order of operations. Remember all this. This is still here in our imaginary world of our brains. But maybe the world in our brains is just as real as the real world. Our dreams are true. I don't know. See, I'm giving you guys the tools to start from true assumptions and then show what must logically follow to also be true. But those true assumptions, they can do whatever you want them to be. It's a free country. I'm not telling you that. All right, so next thing I want to talk about is logical equivalences. Which is analogous to equations in arithmetic. Or equality, maybe I should say. Equalities. So obviously you can have equality in arithmetic like something like a plus b squared equals a squared plus 2ab plus b squared. Now, what do we mean when we write that down? Like, what are we really saying?
I guess if given like the same inputs, they would give out the same outputs.
Exactly. Because here we haven't really specified what A and B are. I mean, maybe it's true somewhere, maybe it's true other places. But like in arithmetic and regular math like we're doing, whenever you see a teacher write that down, what does it actually mean? What this means is, I get red so it stands out. This is true if left and right side of equation evaluate the same number for all, actually I want to put the for all up there. I should say this is true if for all inputs, there we go. So this is true if for all inputs, the left and right side of the equation evaluate to the same number. Meaning, no matter what real numbers A and B I put in here, right, the left side and the right side are going to evaluate to the same number. And that is true in this case, right? I mean, it's weird, though, because arithmetic is weird because there's infinitely many numbers, right? Like, I can check it's true, can verify for some numbers. An example being like let A equal 1 and B equal 3, 1 plus 3 dozen squared equals 4 squared, which equals 16. That's the left side. And the right side is 1 squared plus 2 times 1 times 3 plus 3 squared, which of course equals 1 plus 6 plus 9, which also equals 16. It's going through really quickly. The point is, the left side and the right side evaluate to the same number. But here I've only verified it for one input, the input where a equals 1 and b equals 3. But we're saying this means, what this means to us is that this is true for all inputs, which in arithmetic we can't really verify directly. You have to be a little clever. But for logical expressions, there's only a finite number of inputs, right? Like there's infinitely many numbers, there's finitely many truth values, true and false. So we can literally check it for all of them. So an example of a logical expression would be one that we went over last class, improved last class, and that is not P and not Q is logically equivalent to not P or Q. And same thing here. This is true. True, there we go. If for all inputs, the left and right side evaluate to the same truth value. That's what it means. And so, how can you how do we last time? How do we prove that the left and right side of this equivalence evaluated the same truth values? We got 2 in the chat. TT, I like it. TT, truth table. Yeah, exactly. By showing in the truth table. Can verify this, or I say prove, by verify, that's probably spelled verify, verifying this for every input using a truth table like that. That's what it means for two things to be logically equivalent. That for no matter what inputs you have for P and Q, no matter if P's Q, P's false, Q's true, Q's false, the left and the right sides will go to the same thing. What it means is, since we showed it last time, this literally means that this. I got the skim and almond stuck in my throat. Sorry. What it means is that the left side is just like the right side is just a way to rewrite the left side. They're saying the exact same thing. So for our first test, then, not our actual test, but like a first trial, I should say. Can we find a logical equivalence for this exclusive OR, P exclusive OR Q, using expression written from nothing but just ORs and ANDs and NOTs? Let's think about that. Let's think about that. So what I'm going to do is going to quickly write out the truth table for I'm not gonna write it out yet.
Not P and not Q?
Say it again?
Could not P and not Q work?
Well, let's see.
No, third flip.
So what? Okay, so I'm gonna write down. Here's what OR does. So we have PQ, true, 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 false, false, true, false, false. And what P or Q does is it's true as long as one was true. And then I'm just quickly writing this down. P, Q, P and Q, what that does is it's true if only both of them are true. So there's only going to be one case where that's true. And that's the first case. Everything else is going to be false because not both of them are true. And then we have the XOR P XOR Q. And the options are true, 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 false, false, true, false, false. And this is only true if I can do a better XOR. You guys deserve better. There we go. You're not going to get that tuition money back. There we go. So this is true if exactly one of them's true. So we said it's false in this case because they're both true, but these are both true because exactly one's true. This is false because none of them are true. All right. So these are the things we're dealing with. And of course you have not, which is really simple. That's just P can be true or false, and then not P is false or true. So we want you to think of an expression make an expression from from ands, ors, and nots that is equivalent to P exclusive or Q. So let's think about this. Wait, let's just look at the truth tables. Like, if you notice the truth table here, it's true for the things in the middle, but it's not true on the ends, which is very, 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 very close to or, right? Because inclusive or exclusive or are close. The only difference is their top row here. So P exclusive or Q is exactly the same as or, except in the case where what happens?
Where they're both the same, or where they're both true, not the same.
Where they're both true. So what I'm saying here is that note P plus Q is P exclusive or Q is true if P or Q is true, and what else has to happen? So P exclusive or true, P exclusive or Q is true as long as P or Q is true and something else has to happen.
And P and Q are not true?
Yeah. And P and Q is false. Because notice this condition right here, this case right here, where P is true and Q is true, that's the only condition where P and Q is true. So what we're saying is P exclusive or Q is true as long as P or Q is true, but they're not both true. And obviously, that's what it means. But that's the same thing as saying P or Q is true and P and Q is false. But another way you can write P and Q as false is we can write not P and Q is true. So we want P or Q and not P and Q. This might be confusing, but I hope it's making some sense. The point is, P exclusive or Q is only true if P or Q is true and P and Q is not true. They can't both be true at once. That's all we're saying here. And so the conjecture we get from this, is that P exclusive or Q is going to be equivalent to P or Q and not P and Q. So I think that's true. How can I prove that's true? We are making XOR from scratch. Sorry, I'm just seeing the thing right now. Yeah, so we already defined XOR. We've like made our definition for it, and that's totally fine. But I'm saying that XOR is actually logically equivalent to a particular expression we can make out of operations we already have. Because if you think about it, if you're coding, maybe this saves you some time by calling other methods you already made. But anyway, this is just a little. Exactly. Compare the truth table for the desired result. Exactly. We can show that this is equivalent to this, right? What it means is that we have to prove this by verifying this for every input using a truth table. So we have to verify this side equivalent to this side for every possible input, and we can do that using a truth table. So let's just do it. So I'll say conjecture. Conjecture on P plus Q, that is equivalent to P or Q, and not P and Q. And so the proof will go like this. Let P and Q be statements. And so that's just kind of defining what P and Q are. They're statements, so our options are either P is true and Q is true, P is Q and Q is false, P is false and Q is true, or P is false and Q is false. Those are the four options. These are the possible inputs. And we want to end up comparing is at the end here we want to compare P plus Q, P exclusive or Q, to P or Q and not P and Q. But in order to get to this part right here, we're going to need some intermediate steps, which I'm going to put right here. The intermediate steps is, it would be nice to know what P or Q is. So I'm going to put that just so we have it. It'll be nice to know what P and Q is. And it'll be nice to know what not P and Q is. So these are the inputs. These are the outputs that we want to be equivalent. And then this is just some intermediate stuff. So let's get going. So if P is true and Q is true, right? Based on our definition of OR up here, P, where in this case, so P or Q is true. In the case where P is true and Q is true, so they're both true. Based on our definition of and, where in this case, they're both true. If P and Q is true, if we put that into our not function, so this is like not P and Q, you can think of that. Well, if you put P and Q, when it's true, into the not function, the not function takes a true and makes it a false, outputs false. It just flips it. This is going to be false. Okay. And then finally we get to the end here. If P is true and Q is true, based on our definition of XOR, right, P XOR Q should be false because they're both true. We want only exactly one to be true. And now putting the intermediate steps together here, P or Q is true. This is saying P or Q and not P and Q. Well, P or Q is true, but not P and Q is false, right? This is like saying and the and function for P or Q and not P and Q, right? Which is like, since in this case we know P or Q is true, we can put a true there. Since we know not P and Q is false, this is like doing the and function with the inputs true and false. Well, if you put the inputs true and false into the AND function, what do you get? You get false because they're not both true. So this is false. So the point is, this whole thing right here boils down to false, which is good. That means our conjecture is looking good. So for the first case where P and Q are true, they both line up, right? Their outputs line up. But in order to show this is actual equivalence, we have to show it lines up for all possible inputs. So I'm going to quickly go through the rest of the inputs. Any questions so far? All right, so the rest of the inputs, speed round. So if P is true and Q is false, P or Q would be true. One of them's true. If P is Q and Q is false, P and Q is going to be false because they're not both true. Not P and Q, you flip the false, it's the opposite of that. P XOR Q, or the case where P is Q, so the input is true, false. The true, false input gets us a true right there because exactly one of them is true. And then here, P or Q is true, and not P and Q is true. So if we go to the true input in the AND, we should output a true because they're both true. Both of the things in the opposite on the AND symbol, around the AND symbol here are true, so we get true. We line up again. False, true, we get the same thing. So false, true, in the OR case, where you have a false, true input, we get true for the output because one of them is true. For P and Q, for false, true input, we get false because they're not both true. For not P and Q, we just flip that false to be a true. And then P XOR Q, well, in the case where we have a false, true input, because exactly one of them is true, we get true. And then in this final case, we have P or Q and not P and Q. Well, P or Q is true. Not P or Q is true, so they're both true. In the true case of the AND input, and we're good there. So here, remember, you're literally plugging P or Q, and this not P and Q, those are the inputs to your AND function here. Anyway, false, false. In the case where we have false, false, P or Q is false because they're both false, neither of them are true. P and Q is false because not both of them are true. Not P and Q was the opposite of false, so it should be true. So P exclusive or Q, in the cases are both false, false, we do a false. And then now we look at this final case, P or Q and not P and Q. Well, P or Q is false. And then we have not P and Q is true. So we're plugging false, true into an AND function. And the AND function only outputs true if you plug in two true input. So we're plugging false, true in, or in this case in the AND function, and we get a false. The point is, look at that. The point is, look at this. Look at this. For any inputs, no matter what input we had, true, 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 false, false, true, false, false, our outputs were the same. So, thus, for any inputs, the outputs are the same. P plus Q is logically equivalent to P or Q and not P and Q. Because we verified this equivalence for every single possible input. Any questions on that? It's a little complicated, a little quick, but I hope this idea, I mean, literally, all I did here is mechanically follow the functions OR, AND, XOR, and NOT. And you just made this truth table, and then at the end, compare it. I mean, you can literally write a computer program to do this for you, right? It'd be very easy because computers are built for this exact kind of thing. But I mean, yeah, I mean, you can literally, this is mechanical, right? I mean, you could teach a 4-year-old to just go through and follow these things and then verify it for you. It's meant to be simple because this is the definition. Nothing complicated is happening. But we get a complicated looking result, which is cool. That's what all math is. All math is doing simple, taking a bunch of simple steps to conclude something amazing and complicated. All right. So I will keep moving on. I'm going to go a little over today in the live lecture. But once again, this live lecture is just show up if you can kind of thing. So don't worry about it if you have to leave. And probably by the time I trim it down, it'll be about an hour. But anyway, what's next? So we showed that. Yeah, real quick, let's notice something. Does P and Q equal Q and P? Or are they equivalent? They are equivalent. How can we verify they're equivalent? Truth table. Exactly. We would do the exact same thing we just did. We would prove by having a truth table where we have P and Q. Here are the options: true, 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 false, false, true, false, false. Just like that. Those are all of our options. And then first you look at P and Q, and then you look at Q and P. And then we would be using our function, our big and P and Q definition as a reference where it goes like this. We don't use P and Q, by the way. I'll use R and S here. R and S, S and R. S and R. We're making it a little weird because it doesn't matter, right? There's variable names. And so the way this is defined is like this. All right. So what you do is you go through and you say, okay, R and S for these two inputs, this is the same thing as and R and S, which is equivalent to, in this case, because they're both true, and true, which equals what? Well, when you plug true and true in here, you get an output of true. And then here you get and so first we do S and then we do R, which is, so instead of do RS, do SR, but in this case you would do true, true again, and that would be true. And then you keep doing that same sort of thing throughout this whole process. And then if you do true, false, or if you want to do false, true, false, false, you go through and you go, okay, well, this is and R and S, which is equivalent to and true, false in this case, not true, true, but true, false. When you plug true, false into the and function, you get false. And then here, this is equivalent to not and R and S, but and S and R. You do SR first. So instead of and true, false, we're going to get and S is false and T is true. But it turns out true, false, and false, true give you the same output in the and function. So here, and false, true gives you false. And then you can do the same thing to get false here, false here, false here, false here, to show that yes, they are in fact equivalent. But it's important that we can actually prove this. We don't have to assume anything. We can prove it just from this operation definition of and. This is what the hood of mathematics, this is what the engine of mathematics looks like. A bunch of really simple stuff put together. So even a monkey can do it. Maybe, hopefully one day. All right. So next question. I probably have 10 more minutes. How do we prove two statements are not equivalent? We said to prove two statements equivalent, you check with that for all inputs to get the same output. How do you prove they're not equivalent?
When they do not give us the same outcome.
Yes. So we need to be a little careful here. So we need to show for some input, it doesn't have to be for all inputs, But if for at least one input in the truth table, at least one row of the truth table, at least one of those, the outputs differ, right? Because that's all it means. Because then you can show they're not equivalent because they're not the same everywhere. So an example of that might be prove that P, not P, and not Q does not equal not P and Q. You can't just kind of take a not sign out like that. So how do we prove that? Well, we would prove that by going to the truth table, and we'd have P and Q, and the outputs would be what? Outputs would be what do I need? I need PQ, not P, not Q. These are the intermediate steps. P and Q. And now we're ready for the outputs, which are not P and not Q. That we care about for there. And not P and Q. That's just a bunch of gibberish. Not P and Q. So we just go through and say, okay, here's the possible things. Very repetitive. Not P in the case where P is true is false. In the case where Q is true, we get false. P and Q, well, they're both true, so we get true. Not P and not Q, well, not P is false and not Q is false. So this is the same thing as doing and false, false. And the and function, when you plug in two falses, what's that give you? It gives you a false. So we get false there. And then finally, not P and Q, that's just the opposite of true, which gives you false. So, in the first line, they line up. So if P and Q are true, then the left side is equal to the right side. In order to be equivalent, they have to be equivalent for all inputs. So let's just look at the next input here. The next input, we get true, false. And in the case where P is true, we get a false here. In the case where Q is false, we get a true for not Q. P and Q here, that's going to be false. They're not both true. Think about plugging that into the and function. And then not P and not Q, we think about doing and false true here, because not P is false, not Q is true, so that's what you plug into the and function. Well, and false true, that gives you a false, because they're not both true. And finally, not P and Q, well, P and Q give you a false, so not P and Q would give you a true. So here, they do not line up. Thus, for inputs, P true and Q false, not P and not Q does not equal not P and not Q. So these expressions are not equivalent.
So, Professor, we only need one outcome to answer the question, or do we have to prove it, like we complete the whole table and we mention whatever happened, or just one outcome, odd outcome is fine?
As long as you find one outcome, that's good. So you could do all of these, right? But even if that they only differ in one, like let's say they were the same here and they're the same here, they still differ in one, so they're not equivalent. They don't always give you the same value. So in order to prove they don't always give you the same value, you just have to show that they're not the same once. Does that make sense?
Yes.
Good, good, good. It's like, yeah, it's like, let's say you had a twin brother, and you guys are really like, or a twin sister, you had a twin, right? You two are really competitive, right? And like, on your shared birthday, you always get the same gifts. Well, to prove you didn't get all the same gifts, you just have to show that one of your gifts was different. You just have to show that, hey, you got Pokemon cards, but I got Yu-Gi-Oh cards. That's way worse. Anyway, so that's how you disprove things. Yeah. So that is basically the whole idea of this particular class. This class should have been titled Truth Tables and Approved Things Are Equivalent. So I'm just going to write down at the very end here, I'm going to write down a bunch of expressions, very common equivalences that you can use. These have been proved. I'm going to ask you to prove a couple, and the homework that's due next Friday, not like tomorrow, but next Friday. But other than if I ask you in the homework to actually prove this, you can use these following things, and a couple we've already proven. So here are some famous equivalences. And what I'll do is I'll have their name. That's just what they call them here. I'll have our name, whatever we want to call it. And then I'll have the actual equivalence. So the first one, so I'll say let P, Q, and R be statements. Right, that's just like our, we put that for everything, just so we know what we're talking about. So the first equivalence is P and Q is equivalent to Q and P, no matter what P and Q are. And similarly, P or Q is equivalent to Q or P. This makes perfect sense with how English works, right? Saying I'm going to go to the store and the movies is the same thing as saying I'm going to go to the movies and the store. Maybe I need to use more coronavirus-based examples. How about I'm not going to go anywhere and not do anything? It's the same thing as saying I'm not going to do anything and not go anywhere. There we go, more relatable. So that's what that is. This is called the commutative laws. Anyone have a name for it? The duh laws, okay? The duh laws, sure. Now, it's important to note that even though it's like, oh yeah, they're obvious, it's important to be able to prove it because there'll be things later that you think are obvious that actually aren't obvious. But anyway, commutative. Next, we're going to go with what people call the associative laws, and all that says is that if you do like two ands in a row, it doesn't matter what order you do it in. So P and Q and R, that's just the same thing as saying P and Q and R, and we have the exact same thing with ORs. P or Q or R, exactly the same thing as P or Q or R. Doesn't matter. Anyone have a good name for this? Or associative law, they nail it. So quick Q, is that our name? Oh, quick question. Yeah, sure. What do you got? So the questions are, so do we not do Boolean shortcut circuiting for the ands? Oh, yeah, you're very right. Sorry, Sid pointed out that this should be a P. Actually made an R, very good there. Okay, so Benet asked, do we not Boolean shortcut circuiting for the ands, meaning if the first is false, it doesn't matter what the others are. Oh. When actually evaluating, you can totally do that. That's true. But here we're just talking about equivalences, which is kind of It's kind of like the difference. It's kind of like, yes, it's true in arithmetic. It's like, yes, it's true that A times B times C equals A times B times C. We want to write that law down. It works for any single numbers you put in there for A, B, and C. But it is true that if one of them is 0, you can just skip all this because it's going to be 0 for evaluating. But in terms of equivalences, we want to make it work for all cases. And so this is just what we're showing here. Hope that makes sense. So, associative law, let's call it the parentheses party or something, I don't know. This must be for you guys, whatever you guys think makes more sense, because some of these are going to start sounding weird. All right, this next one is the distributive law. And what time? Oh, we gotta go. Distributive law, all that says is that P and Q, no, I'm sorry. That says that P and Q or R, this is gonna be just like distributive with multiplication and plus. You're gonna distribute that and through here. That's gonna be P and Q or P and R. So we kind of distribute the and to the Q and the P and to the Q and the R. And then same thing for the other way around. It's true that P or Q and R, that's going to be equivalent to distributing the or, the P or to the Q and the R. This is going to be P or Q and P or R. All right, if no questions, I'm going to move on. Next, we have the identity laws. Actually, they're just going to do the De Morgan's laws. These are important. So De Morgan's laws are really cool. We actually already did one of them. And they go like this. They're a way to deal with these negations and make something new and interesting. So not P and Q is equivalent to not P or not Q. So you can distribute this negative, but when you do, you flip the and to an or. That's going to be very useful and very interesting. You might say this looks familiar. That's because we proved the other De Morgan law, which says that not P or Q is equivalent to not P and not Q. Totally true. These are De Morgan's laws. You're going to get questions on this. You're going to use it in the homework. I think these 4 are the laws you're really going to use a lot. These are the ones that really come up. De Morgan's laws, distributive laws, you're going to have to prove that these work in the homework with truth tables and all that. And next we get into kind of the weird ones. So the idempotent laws, they just say that P and P is equivalent to P and P or P is equivalent to P. By rethinking naming those the duh laws, right? Let's just name these the solo laws. I don't know. Because there's no Q here, it's just solos. And this should make sense to you, right? If you say, I'm gonna go to the store and I'm gonna go to the store, the same thing as saying I'm gonna go to the store. Oh, how do you spell that last one? Sorry, yeah. This is, De Morgan or idempotent? Oh, you nailed it. Good job. Yeah. Idempotent. I-D-E-M-P-O-T-E-N-T. I have no idea why. There's also things called idempotent matrices, and I don't actually know how they're related. Oh, maybe I do. Actually, it kind of makes sense. Okay. Next, we have the double negative laws. This is just easy. This just says that not P. Guess what? That's P. Right? Super easy to prove with the truth table. And then finally we have identity laws. Now this is kind of what you were talking about. Call that one psych law. Like it. Psych law. So the because not P, psych is just P again. Identity laws, they are really simple. P and something true is just the same thing as P. Wait, that's not where that goes. Yeah. P and something true is just the same thing as P. And then P or something false is just the same thing as P. Because if you're ANDing with something true, well, in order for this statement to be true, we just need P to be true. But if P is false, the statement's going to be false. So it's just exactly what P is. Here, if you're ORing with something false, well, the false thing can't really help you. So P's got to be true for it to be true, and if P is false, none of them are true, so it's false. And this can be proved with the truth table, really easy. And the last one, I'll write down right here. It's called the universal bound law. And all that says is that P or something true is true, and then P and something false is false. I think that makes sense. Because P are true, well, one of them's true, so you're true. P and false, one of them's false, so you're false. Washing a pile of mud law. Yeah, this all seems very simple, but if you're actually looking at doing mathematics from the ground up and proving everything from very simple assumptions and definitions, right? This is a new and interesting thing. This is not in the definition. This has to be proved from a definition, right? This is not a definition. This must be proved from definition. And then you can build this really simple rule, and hey, that might be useful somewhere else. So you use this to build another rule. You use that to build another rule. And then all of a sudden you're doing interesting things like calculus and stuff out of nowhere. So, yeah. These are the laws. Any questions on the laws? You can use any of these. You don't have to prove them when you use them. Just tell me which one you're using. Just say, like, by the commutative law, we know this is true. By the distributive law, we know this is true. But you have to tell me what law you're using when you're using it, and we'll talk about that more later. The only time you'll ever have to prove this is if I specifically ask you to prove the distributive law. Okay. So, to end, there's two very simple definitions that I don't even think they'll come up, but in case you guys take another class and they come up, I want you guys to know. And that is, what are they called? A tautology and contradiction. So a tautology, this is T-A-U-T-O-L-O-G-Y, tautology, yeah, is any expression that is always true. Example being P or not P. One of those is going to be true. If P is true, well, this statement's true. If P is false, not P is true, so this statement's true. This is always going to be true. You can prove it in a truth table. It equals true no matter what. So it's a tautology. Definition, contradiction is any expression that is always false. The exact opposite. And the way that goes is, an example would be P and not P for the same reason, right? If P is true, then not P is false, so this whole thing's false. If P is false, well, this whole thing's false. So that's just, these are just two terms that you might see somewhere later. Maybe not. It's fun vocabulary. And that is it. Class is over. Any questions, anybody? Sorry for keeping you late. I mean, you could have left any time, but you know, you guys probably want to see. So sorry for keeping you late. And Yeah. I'm gonna stop recording. This class is over. Alex.